an inductor, you got some resistance just from that wire. And that's something that we haven't really dwelled on too much since chapter 27, which I know was the last task, but I know you've been reviewing for the final, so that's not at all foreign to you. You're like, oh yeah, I know long wires have resistance. So that's what this part of the problem is trying to say. Then, of course, there's another resistor hooked to it with 14. And it might be easy to overlook this 24, but I would say that what I really have is two resistors in series. And what's the equivalent resistance of two in series? Yeah, and so if I add these two together, I get 38 ohms. And so one of the things that makes probably this problem a challenging one is to not only realize it is an LR circuit problem, but to realize then there are two resistors in series, and I got to put them in series to realize that the equivalent resistance is 38 ohms. Now, the other part of this is to say, well, what's the inductance? Which, for a coil, we worked out in class. So either A, you can memorize it, or B, we could go through a couple calculations. And that's probably best. Otherwise, we'll find ourselves memorizing too many equations. As I said, if you find yourself trying to memorize a bunch of equations, you're missing something bigger here, that there's just a couple of fundamental equations, which, by the way, that's what Tuesday, I think, makes a nice last lecture, because I'm just going to summarize the whole semester. And you'll see everything we've learned can be wrapped up into 4 equations. So, you know, if anybody ever asks, just say, well, what'd you learn this semester with 4 equations? And you can say, that's it. Yep, that's it. I can all write them on the palm of my hand, but don't during the test. All right? But it's really about, physics is about how a few fundamental, powerful ideas explain a universe of phenomenon. And so we really just have these 4 equations that we will summarize on Tuesday here. So, like I said, you may or may not remember it. I don't remember it, so I need to go back and re-derive it. I know this, that the magnitude of the EMF is equal to the change in flux. Also then times how many turns you have. And so if you take something like this coil here and you go to calculate the flux, you'll have to take N, that's the induced EMF, so how many turns do I have? Well, according to this, I have what, 820? Is that what I remember reading? And I've got 820 of them. But then I have to calculate the change in the flux. And the flux is that B dot dA, and so I'll take the dot product. And then I got to remember something about coils. And of course, we did learn something really nice about the coil, or the solenoid, or the inductor. Well, I shouldn't say the inductor could have any shape, but this one has the shape of a coil. That's why it says coil, not just inductor. But the coil then has a uniform magnetic field in it. And so that's really nice. I can pull it out of the integral. And the other nice thing is that the field went right down the tunnel part of the coil. And so the angle between B and A is 0 degrees. And so this just becomes the area of where there is flux, which is the tunnel part. And of course, the other nice thing we learned about a solenoid is that the magnetic field from a solenoid is mu naught times what we call the turn density times the current, and then times the area. And so if I rewrite this equation, I can put the two n's together, so there's n squared. Then I can put the mu naught. Then I can put the area. Then I can put over L. and then I get the di dt. And if you compare that to what we've been doing with our inductors, we've been saying the voltage from the inductor is minus L di dt. Now I didn't put the negative in here, just like the last problem, but maybe I should have. So if I'll take away the absolute values and put in the negative, you will hopefully see, and this is how we introduced the chapter on our LR circuits, was to say that if you took Faraday's law and applied it to a back EMF on itself, then you would get this little equation for the inductance for a coil. And so we did the inductance for a coil. I think you had a homework problem that had you do a toroid, if I remember right. And I think it's coming up as a test example here soon too. So we'll do this again for the toroid. But this is for the coil. And so these numbers I can put in. So this is the 820 turns. This is the 4 pi times 10 to the negative 7, the permeability of free space. The cross-sectional area was given in this problem. 1 times 10, and let's be careful with the units here. 1 times 10 to the negative 4, but then it is centimeters squared. So that centimeter squared would make another 10 to the minus 4 in terms of square meters. So here's one where you always want to be careful with your units there. And then the length of this thing is, how long is this? 7 centimeters. And so that's 7 times 10 to the minus 2. So if I grab my calculator here and go 820 and square it, and then go times 4, and then times pi, and then times 1 times 10 to the negative 7, then times 1 times 10 to the negative, and I might just put all these together, negative 8. Then divided by 7 times 10 to the negative 2, I get 1.21 times 10 to the negative 7 henries. It's pretty small. But that's a really small area. All right, but anyways, I think that number's right then. And
yeah, that's what they have.
Is that what Don has in the solution? Good.
1.207.
Okay. So there's the inductance. And that might be the hardest part of this problem, is realizing, hey, this is an inductance problem. Because now the actual current itself, we worked that out in class, and you can rework it again, but I think the best thing to do on this one is to remember we did that time constant. It acts just like the capacitor, where the time constant was this L over R. And so now I've got a little bit more math to do, because they say how much time does it take for the current to reach half of its maximum. So its maximum is V over R, and so you want it to reach half of V over R. Of course, we also know V and R, so we could actually do a number, but I'm going to avoid putting in a number just because I notice on the other side of the equation there is a V over R. And so V's cancel and R's cancel. And so if I move this over to here, I get e to the minus t over tau equals 1/2. And so now, No, let's see. If I move this over to here, then I've got 1 minus a half. Yeah, it's 1/2. And then I can now take the natural log of this. And so minus t over tau is then equal to the natural log of 1/2, or t equals negative tau natural log of 1/2. And tau is this L over R natural log of 1/2. So here's the negative, and the L came out to be a really small number. The R, which we talked about earlier, is the 38, not just the 14. And then the natural log of 1/2, fortunately, is a negative number. I was getting worried about that negative in front, but now I see where it's going to have 2 negatives in it. And so if I take 1.21 times 10 to the negative 7 and divide it by 38 and multiply it by the natural log of 1/2 with a negative, is 2.21 billionths of a second. So, and is that what the number they got? Yeah, so incredibly small number because this is an incredibly small area. I can't help but think that was not meant to be both there. Maybe that or just that, but not both. But nonetheless, there's got to be more realistic numbers that we're used to working with our real numbers in the lab. Should we do another one and break? Should we break now? One more? All right. One more? All right, we'll finish the whole. Yeah. Well, let's do one more, and then we'll call it we'll call it break time. Yeah.
Is there another way to find the conductance? Could you do the N flux over I?
Yeah. Wait. So talk to me. Do what? N?
Yeah, it's the other formula for inductance, which is N times flux, magnetic flux over I, right?
Yeah. Yeah. Okay. Yes.
What would I be at that point?
Well, yeah. I don't know if you could do that because we don't have enough information. Because what you're saying is, and forgive me, I just kind of think this through, but you're saying this is how we might write Faraday's law when applied to a circuit up on itself, right? But when we apply it to Lenz's law, not Lenz's law, Faraday's law, we have that. And I think what you're saying, if you integrate both sides, you get number of turns times flux is equal to inductance times current. And so the inductance would be number of turns times the flux divided by the current. Oh, that's what you were saying.
Yeah.
Okay, I don't disagree with that. Oh, then you might do this. Okay, I see. And you would then say, all right, let me leave the number of turns and the I alone. The flux then would be coming from this being a coil. And so that would be the magnetic field times the area. And then the magnetic field from a coil would be mu naught times N over L times I times A. And then, of course, this I over here means that would cancel. And I think we have it. We have an N squared, a mu naught, an A over an L. And that's the same thing, right? Yeah. So, yeah, you could certainly do it that approach, too. Yeah. They're fundamentally the same thing. They're both starting with Faraday's law applied upon itself, and that's where I did this. Yeah, so
I think you might have erased it.
I think I erased it, but it started over here, Faraday's law onto itself. Yeah, yeah. So, and maybe that's more efficient. Maybe that would have been a better approach for this problem. All right, so let's try number 4 here, and then we'll take a break, and I'll leave us with just 6 more to do here. Let's see. This one says, consider a series RLC circuit. Okay, so this is getting closer to the stuff we've done just last week. And these are the following parameters. So they give you the resistance, they give you the inductance, they give you the capacitance. The applied voltage is sinusoidal and it has an amplitude of 50 volts. It has a frequency of 60 hertz. What is the maximum current and the phase constant relative to the applied voltage? And so we spent a lot of time talking about this conceptually, but let me start there. And say what we learned was that for high frequencies, the inductor, because of Faraday's law, opposes the currents. Maybe I should start using the word impedance more. We just got at the last part, but the overall hindrance to the current comes from the inductor, the capacitor, and the resistance. You have the reactance from the inductor, you have the reactance from the capacitor, and you have the resistance from the resistor. And the 3 of those are opposing the current for different reasons. And the inductor uses Faraday's law. And so high frequencies are opposed more than low frequencies in the inductor. The reverse is true for the capacitor. The capacitor opposes the low frequencies. The resistor opposes all of them equally. And so when we put all those together, we said an AC circuit hooked to an inductor, a capacitor, and a resistor then would have a current that flows through it according to this equation. It was the maximum voltage divided by the whole opposition. The reactance of the inductor, the reactance of the capacitor, and the resistor. We called that the impedance. And then, of course, there was the sine or cosine. I'm trying to remember, what did we use? Did we use sine or cosine? I guess we used sine. Sine, yeah, sine. Omega t. Where then the voltage was out of phase by some phase constant. And as I tried to show you a number of times on the oscilloscope, and it's your lab next week, you are going to hook it up and you're going to play with those dials like I was, and you are going to first do a high frequency, let's say. And at a high frequency, you'll get more of the Eli effect. You will get your voltage before your current. And then at the low frequencies, you'll get more of your ice effect. You'll get your current before you get your voltages. And then that magical one, the one where the inductor and the capacitors are equal in magnitude, they're always opposite, will then cancel each other off, and the whole thing acts as if there is only a resistor in there. And so that was our discussion here, and then it was a long derivation and my chance to introduce you to phasors. I wouldn't expect you to have to go through the whole phasor derivation for the test, but do want you to remember then the impedance had the resistance, the reactance of the inductor, the reactance of the capacitor. They were opposing each other, so they were opposite. And those were both cosine functions that we had to add to a sine function. And so there was our impedance. And that's exactly where this one comes in, because it says here, find the maximum current. And you got to be careful with that phrase, maximum current, because the current right here changes with time. And so this out in front is the maximum current for that given frequency, because the maximum current changes with different frequencies also. And so when they say maximum, they mean maximum of time, not of frequency. And so they give us the frequency, I believe. And so let me find the impedance here. And so given the numbers that they gave us, I would say, what is the resistance? All right, 200. So there's 200 ohms. What is the reactance of the inductor? Well, that's the omega L. And so they gave me a frequency of 60. And so this would be 2 pi times 60. That's the omega. And then let me give me the L. The L is 0.663. And so there's the reactance from the inductor. And then for the capacitor, remember it's 1 over omega times C. And C in this problem is 26.5 microfarads. So 26.5 microfarads. And I'll square that. And so maybe I'll just do an intermediate step, 200 squared plus, and it might be nice to find out these individually. So 2 times pi times 60 times 0.663 comes out to be about 250 ohms. So I'm getting 250 ohms of reactance from the inductor, although it's being canceled a little bit by the capacitor. I don't know how much. Let me try it. 2 times pi times 60 times 26.5 times 10 to the negative 6. Then I'll take the reciprocal of that, and so that's about 100. So I'm getting a lot more reactance from the inductor from the capacitor. So this would tell me that I'm at a high frequency range, right? Those two are equal at what I called the magical or the Goldilocks frequency. And so they're not quite matching up. This is not quite at the what we might call the resonance frequency or the magical frequency or the Goldilocks frequency. But it is what it is, and that's the number I have. So I have 200 squared added to 150 squared, and then taking the square root of all of that, I get 250 ohms. All right, so that's the total impedance. And so to get the maximum current, I would take the voltage at its maximum and divide it by that impedance. So we're talking 200 and, whoops, wrong place for that. 250 is the impedance. 250 ohms is the impedance. And this AC voltage source has a maximum of 50. So that's 1/5. So it looks like 0.2 amps. And so that is part of this problem. Find the maximum current. But then it says, and also the phase. Now, of course, I just noticed that I have more reactance from the inductor than the capacitor. So this is more of an Eli effect than an ice effect, which tells me then this ought to be a positive number. And so the last part of our phasor diagram was to say tangent of the phase is equal to the difference of the reactance over the resistance. Because our phasor diagram looks something like this. You had the resistance here, then you had the reactance of the capacitor, and then the reactance of the inductor. And so if you added those three together, this right here would be the reactance of the inductor minus the capacitor. And so I can put in my numbers. This is what we just said was 250. This was 100, and this is 200. And so to get the phase, I'll just make sure I'm in degrees here. I have the inverse tangent of, and that's going to be 150 over 200, and that's 36.9 degrees. And so I get voltage a little bit before current. Again, which hopefully makes sense. This is acting and dominated more by the inductor. And I don't know if I should say dominated by the inductor, because the capacitor is taking off a little bit of the inductance, and so most of it is actually resistance, but then there's quite a bit of a reactance from the inductor, not quite balanced off by the capacitor. All right, well, let's take our break, and we'll regroup. How long do we break? 15 minutes? Only 10? It's getting late.